Okay, so let's try and apply some of these ideas of data analysis, and let's imagine ourselves to be in the shoes of Galileo, and let's say that Galileo somehow has access to Mathematica, and then we design a thought experiment. So we of course know that if you drop a ball, then the distance covered by it as a function of time is just half gt squared, right? So what I'm going to do is use Mathematica to give me some data, right? I mean, I'm imagining carrying out an experiment in which I drop a ball, and then after a certain, let's say after 1 second, I find out how much distance has it covered, after 2 seconds, how much distance it has covered, after 3 seconds, how much distance it has covered, and so on, all the way up to 10 seconds, right? And then, so this is going to give me one set of data, and then I repeat this experiment a second time. Once again, I will get another set of numbers. It's not going to be identical to what I had the first time, but it's going to be roughly in the same ballpark, right? Then I do an experiment a third time. Then again, I have a bunch of 10 numbers which are all different, but very close to the the first set, and so on. So you could imagine repeating this experiment a large number of times, right? So this is in the spirit of how one carries out experiments, right? So suppose Galileo had no idea that there is a quadratic relationship between time and distance. Just by carrying out this experiment, we don't get into how he would actually measure these distances. Suppose it were possible. So in principle, one should be able to extract a neat quadratic curve, right? And with error bars, right? So the focus of this current discussion is all about how to do statistical analysis of this. So in order to do this, I am going to find a way to use Mathematica to give me some data. It's fictitious data. So what I will do is, so first of all, define gravitational constant as g equal to 9.8. Of course, I already know the functional form to be half gt squared. So what I will do is, I have this code which I will just first run this whole code, and then I will explain to you how I am generating this, right? So basically I'm telling you that if I were to use this entire code, I can generate a table where after 1 second, maybe the ball has reached the distance 5.72 in meters, right? So then after 2 seconds it's at 19.98, after 3 seconds it's at this, and so on. After 10 seconds it's 549.87. But if I were to do the experiment the second time, you see that the numbers are slightly different, but they're all in the same ballpark. There's a spread, and this spread is something that I have used Mathematica to generate, right? So what am I doing here? So you see, whenever you see code of this kind in Mathematica, the correct approach is to sort of go inwards out. So you start with the simplest function. So I've already described what table does. So I'm using something called round, using something called random real, I'm using something called Prepend. These are all functions which Mathematica has inbuilt in them. So I will let me try and open it up for you. So I will start with, let's say, just round. So if I were to go down here, okay, so I will use input. Okay, so if I were to do round of 9.789645, let's say, and if I want to round this to 0.01, and I go ahead and hit shift enter, so it gives me an answer of 9.79, right? So which is what you expect. Up to 2 decimal place accuracy, 9.789645 is 9.79, and that's what Mathematica tells me. So here I want to generate this data, half gt squared, and I want to put this in a table, but I don't want only half gt squared. I want half gt squared, but with a spread around it with a random real. Random real is a function which gives me random numbers in the range 0 to 1. So if I do random real, and it doesn't require any. So if you don't put any arguments, it means that you're looking for a number between 0 and 1. So there you go. So it gave me 0.8. If I were to repeat this, it would give me some other number, and so on, right? It gives me some bunch of numbers. So what I'm asking Mathematica to do in this code is to generate a number close to half gt squared. So you see, I goes from 1 to 10. So this table generates for me a bunch of numbers, and so I get it's supposed to give me half gi squared, where I will go from 1 to 10, but I also ask it to give me some spread, which will going to be like 20% of this value. I mean, I've just put some number, like some fraction. I have taken it to be 20%. You could try it with some other percentage. You could make it a constant error or constant spread of some kind, but I am choosing to make it to be a percentage of the value itself. Let's not go into whether this is exactly how a real experiment would give or not. I'm just playing, right? So when we're playing computer games, we are free to choose these parameters, and so here I'm choosing it to be 0.2. So later on, of course, we can go back and change this, and in general, one can make it a parameter with which you can play with, and you can study it more systematically and so on. But for our purposes, we are doing something very simple, right? So we're generating a table of numbers which are in the ballpark of half gt squared. Then I nest it around with another table. Why do I do this? Because I carry the same experiment 10 times. So that's the second 10 that you're seeing, right? So let me try and explain this step by step. So the first table. So if I've told you that if I were to generate a table of some numbers, let's say I, and I goes from 1 to 10. It's going to just give me numbers 1 to 10. And then if I were to put another table around it, so Mathematica is going to say I need to generate this entire table itself so many times. So if I were to do 10, it gives me an array of arrays. So here, of course, I'm doing something really dumb, because why would you want these numbers from 1 to 10 repeated 10 times, right? But on the other hand, so in the experiment, or that I'm trying to simulate, what I'm trying to do is get some spread. So it's not going to be just the same numbers again and again, but because I have random real, I'm going to get so many different realizations of this, right? And then round, make sure that these numbers are always cropped in a nice way, and I have only 2 decimal place accuracy. And then finally I have this. So let me just try and explain this prepend. So before suppose I did it without prepend, it's going to give me something like this. Let me copy this stuff and paste it here. It's going to give me data which is going to look like this. Let me put it in. Table form is just a nice form. It gives your data. So if I did not do this, then I have these numbers, after 1 second, 2 seconds, 3 seconds. So it's along the horizontal axis. It's increasing, right? So, but I would also like the time to appear right at the beginning. So what I do is use this thing called prepend. If I were to do prepend, if I do prepend, Prepend, and then put this entire thing around it, prepend, then I have to provide this range. It's numbers ranging from 1 to 10. If I do this, and then again table form can stay as it. So now you see that I have these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 right at the top. See, at the moment I have it arranged in this sort of column wise, but I want this to become row wise, and that's why I also do transpose. I use this thing called, it's a post processing operation. So if I do / and then do transpose, then that's my final answer. Or I can also, of course, go ahead and do transpose of this entire thing. That's going to be the same transpose of this whole thing, and then look at it in table form. That's this, right? So this is exactly what I have, but I have used the other approach to do transpose. And then finally I want to store all of this data in a variable which I'm calling it data, so that I can use this this variable itself later on, right? To do my analysis, I'm going to be working on data. Okay, so I'm going to erase all this. So this was just some explanation of all the steps involved in working out this code. So let me remove this. I would be cluttering it otherwise. But what I just did is also illustrative of how one looks at mathematical code, or code in general is to be analyzed as, you know, bits and pieces. You take them apart, you pull them apart, you ask what is each individual bit doing, and then you try to integrate them. And when you're integrating them, you must figure out how to make it compact. On the one hand, the code should be you know, as clean and as minimalist as possible, but it must also be efficient, right? So these are things that you would pick up as you go along. Where the more you code, the better you become. All right, so data, once we have, we want to look at it with this table form. So let me just implement this whole thing again. I have this data, and then I will also do table form. So it's already there. Table form is also taken care of. Finally, when I have all of this data, I might want to export this entire data to my desktop, for example, or somewhere else. And so this is the syntax. We have already seen this, and then I could do this and then again import it back, right? You could pretend for a moment that all this information was obtained, was got from some experiment, and so then you would just start from this step alone, right? You don't go do this whole business of getting the data. We created the data using Mathematica, and next we're going to analyze the data using Mathematica. So in some sense, all that we did so far is an artificial way of generating data. So far we have not really applied the concepts that we discussed earlier. So in some sense, only what follows is the critical aspect. So far it was some tricks to generate data, you can say, or it's a method to do simulation, right? So we might get into a systematic discussion of simulation techniques at a later time, or maybe in a more advanced course. But for now, all we want to do is actually to be able to interpret data, right? So we have you know, all the data is stored in this variable called data1, but let me just do my analysis on my data, right? So now there's more syntax. So suppose I want to just look at, let's say I'm interested in looking at some particular number. So Mathematica tells us that your variable, you have access to any column and any row, and in order to do that, this is the, suppose I want to get the first row, first column data. This is how I would do it. I would take data of, so I would have to put this inside the, enclose them in two brackets of this kind, and then if I want to go to 1, 1, and then if I do shift enter, then there you go, you have the number 1 appears. So if I had done 1, 2, then I have 5.15, right? Again, not a surprise. So it's the first row, second column. Now, but suppose I want all the columns, but in the first row, then the syntax for this is to do this. So I can go from 2. So if I were to go from second column to third column, then that syntax is this. So the starting column and the ending column should be separated by these semicolon and semicolon. So if I do this, I have 5.15 and 5.68. So if I wanted information from second column all the way up to fourth column, then I would do this, and I have these 3 numbers. And if I want to go all the way till the last column, I could of course just specify column number 11, right? Or I could just leave it blank, and it's going to give me data for all the columns, right? So I'm interested in this particular number. So this is just to illustrate how I can I can go ahead and compute the average of this, right? So after all, what are we interested in? We are interested in doing data analysis row by row. After 1 second, I want access to the mean and the error bar, right? An estimate of the mean and an estimate of the error in my knowledge of the mean, right? If I have this information, then I can go ahead and do further data analysis on this. Now, so let me call this whole quantity as set, right? If I put a semicolon, it doesn't show all the numbers, but it's stored there. I have to still implement it. So I can go ahead and compute the mean of this. So mean of this is simply the average of these 10 numbers, right? So I mean, so you see that I go from 2 all the way up to the last column. The first column is suppressed because the first column is date of the time. It's only from second column onwards that we have information about the distance. So the mean is 5.397. So after 1 second, the mean distance covered by this fictitious particle is 5.397. So then we also have this length of set is a useful useful function. So it just simply tells you how many data points do you have. So of course we know that there is 10 of them. So let me compute this. So if I were to do mean, I get this. I could have also done length of this. Not a surprise that it is 10, right? So I want to use, so you remember that you must find the sample mean is the mean of the distribution, and the sample standard deviation divided by square root of n minus 1 is a measure of the error bar. So that's what I have here. I have square root of this, square root of n is nothing but square root of length of set minus 1, right? It's the square root of this whole thing. That's what I have down here. So let me change this back to mean of set. Then I have standard deviation of set divided by square root of length of set minus 1. I can go ahead and find out this number. This is what the number is. I can also suppress it. So let me get rid of this cell. I can redo this just to check that it's all good. There you go. And then I will suppress this. Okay, so then what I want to do next is actually carry out this kind of an exercise for each row, right? Ultimately, what do I want? I want to have, so I know how to do the data analysis, but I want a compact, quick way to do this data analysis row by row for each of the times. So there's again recourse to this table command helps. So we will do set not just for the first row. So let's say that we are doing this set is equal to data of the nth row, and again columns going from 2 all the way up to the last column, and I will call it set. So table is a new array which I'm defining as mean data, right? It's going to have the time n will go from 1 to 10, and it's going to have the mean of the set, and it's going to have the error bar. So error bar I know how to compute, which is just simply, so in fact if I want to clean this up a little more, let me copy this or cut this and call this right. So I have defined something called error or error, and so at each step it's going to compute the error, and then I have to store this information. I want to store the time at which I'm doing this, carrying out this, finding out the mean, and then the mean and the error at that particular time. So if I were to just run this, yeah, so there you go. So I have 1, 5.37, 397 and 0.1 and so on. So finally I want to put this in a nice form, of course, right? It doesn't look so nice if it's just the way it is. So you go to table form of mean data. So then you see that after 1 second it is roughly around 5.4, and then it has with errors of 0.1 and 21 bigger errors, and so the errors also grow because that's the way I have set it up, right? So you could have set up a different model where the errors are roughly the same, but so that's a whole different discussion altogether. But suppose these are these are the numbers, this is the way to do the data analysis. So now the final thing to do is, of course, to make a plot of all of this, right? So this last piece of code you should study a little more carefully, and then you'll see that this again using the nested argument. You start from the table command, you start with each of these different functions, and then use them to, in a judicious way, you can get this mean data. Final thing is you have to load something called error bar plots if you want to plot this with error bars. And then okay, so it's not clear whether this is going to show up. Yeah, it does show up. So is now obsolete. There is a new version of this available, so we can work this out, we can figure this out. So but anyway, it seems to work. So there is some comment that Mathematica gives us, but even so this is working out all right. As you can see, the error bars are there, but they are not so visible because they're too tiny. So let me, in order to just exaggerate how these error bars are, I'm going to just put in a factor of 10, right? It's a common factor of 10 for all, and to show you how the this is going to explicitly look like errors. Yeah, so there you go. So this is what one might see in a real experiment, but of course these numbers are exaggerated here, and also you see that the errors are changing as a function of time, which may or may not be the way a real world system works. So anyway, so the whole point of this discussion is not really about whether the model we have for generating these errors is the right one or not, but it's simply about doing data analysis, and to illustrate how with Mathematica there is a quick and powerful way to take up all this data and to analyze this using our method, and then to make a plot. So the key main message to take from this this lecture is that if you have a bunch of repeated experimental data, then the average of all of these numbers is a good estimate of the mean of the distribution, and the standard deviation of the sample standard deviation divided by square root of n minus 1, which if you have a lot of points you can just take it to be square root of n. So sigma divided by square root of n is a good estimate of the error bars, and with Mathematica we are able to extract all of this information and get an error plot with error bars in a nice compact way. That's this lecture. Thank you.